This is my final talk on random error, and I'm going to be talking mainly about confidence intervals. But let's start with p-values, because confidence intervals are an alternative to p-values in some ways. So first of all, thinking about p-values and their limitations. So p-values that are produced by a study are affected by two main things. One of them is the size of the association between the exposure and the health outcome. Now we don't know that before we carry out the study. The other thing which we do know is the sample size. But our ability to detect an association between the exposure and the health outcome is very much affected by the sample size. So these two things are not independent. But p-values alone don't provide any indication of the size or magnitude of the effect, or the possible range of values, because as we saw in a previous talk, then if you were to repeat the study many times, which is a hypothetical thing really, because we don't actually do that, but you would potentially get some variation in the result just because of the variation in the sampling. So although we produce some sort of measure, some relative risk estimate from our study, it might have been slightly different if we had carried out the study twice or a second time. So provides no indication of the size or the possible range of values. Secondly, they are very much affected by the sample sizes I've talked about, and in themselves they don't provide any indication of the adequacy of the sample size. So I think that in many ways illustrates the problem of people applying this arbitrary criterion of a p-value of less than 0.05, which is really, as I have talked about before, a decision-making criterion. So all of this, I think, illustrates the value of confidence intervals. Confidence intervals, they avoid this issue of making decisions, because in epidemiology we're much more interested in measuring effects than making decisions, measuring the size of effects than in making decisions. So, and we know that our measures of association, which might be relative risk, say, they have some variability dependent on the sample. So we really need to be able to kind of capture that in some way. And we do that using confidence intervals, which is a range of possible values around the point estimate that we obtained in our study. Point estimate, of course, being the relative risk or the odds ratio or the risk difference, depending on what we're looking at. So the confidence interval gives us some measure of the precision of the parameter that we're looking at, such as the relative risk. And you can say that all values within the confidence interval are basically consistent with the data obtained in the study, and they're all plausible. So we might express the confidence interval in this way. This is just completely a random result. It could be any result, just to illustrate. So we often express the results like this way: the relative risk, or an odds ratio, 2.63, 95% confidence interval, 0.85 to 5.27. In this example, this is just an arbitrary random example, but this is just basically how we display the data. So how do we interpret that? So we can say an interpretation that's, I think, generally accepted by pretty well everybody in epidemiology and biostatistics, is that if, hypothetically at least, you were able to do the same study 100 times, so sampling the population, and of course each time you get a slightly different sample, in 95% of the 100 results, the 100 sample results, the true parameter, in other words the relative risk, would lie within the 95% confidence interval. So I'm talking about there the true parameter. This is the true parameter is the parameter in the population itself. But in five results, the true parameter would lie outside the confidence interval. So we can illustrate this as follows. So this is only 10 results, but we could have 100. And so you can see, now this is the truth. Mu, Greek letter mu, represents the true value, the true relative risk in the population, which we don't know, of course. But we carry out a study. One of these studies represents our study that we carried out, we don't actually end up carrying out multiple studies, usually. But this kind of represents the situation if we were able to carry out multiple studies. So, and you can see that in this situation here, only one of the studies actually, the confidence interval excluded the true parameter. So that's why we say that if we carry out the study 100 times, in 95% of the times that we carried out the study, then the true value would be somewhere within the confidence interval. So this represents the point estimate, and this represents the confidence interval here. So this is, I think, a good way of kind of describing what confidence intervals are. So how do we relate confidence intervals to p-values? And so it depends. And it depends very much on whether the confidence interval includes or excludes the null value. And so with relative risks and odds ratios, the null value is of course 1. And if the 95% confidence interval that we get from our study does not include the null value, then we can say that this is equivalent to a p-value of less than 0.05. So here's an example. The confidence interval does not include 1, and so this would be regarded as a statistically significant result. On the other hand, if one of our boundaries of our confidence interval was 1, then we would say the p-value is exactly 0.05. And so we have these two situations that we could obtain from our study result. One of them is where the exposure seems to be a risk factor, and so the lower confidence bound is 1. And on the other hand, there's a situation where we might find apparently a protective effect, and in that circumstance the upper confidence bound would be 1. And in both of these situations the p-value would be usually exactly equivalent to 0.05. And then we have the other situation where the confidence interval includes 1, the null value. Then we can infer that the p-value, the corresponding p-value, would be greater than 0.05. So these are the three general situations that we find with confidence intervals and p-values. But we'd usually say that the confidence interval was more informative, generally speaking, than the p-value. And this next example illustrates it. So, say we're investigating the relationship between diethylstilbestrol, sometimes referred to as DES, and breast cancer risk. So, DES was given to women back in the 50s and early 60s who were threatening to spontaneously abort. And it helped to prevent abortion. It's basically a synthetic estrogen, but subsequently it's been shown to be the cause of various health effects, particularly vaginal adenocarcinoma in teenage girls who were the babies whose threatened abortion was prevented. So it's an example. The only example I know of, in humans anyway, of a transplacental carcinogen. So the mother takes the DES, but it's the baby which experiences the health effects. So this is a study of breast cancer risk. So the study obtained a relative risk of 1.4. The confidence interval was 0.7 to 2.6. So how do we interpret this? We can say that the best estimate of the increased breast cancer relative risk associated with DES is 1.4. And we can say that the data are consistent with hypotheses that the true relative risk is between 0.7 and 2.6. In other words, the fact that it's elevated above 1, it could be just a chance result. So any of these relative risks between 0.7 and 2.6 are basically compatible with the data. So that's somewhat informative. It's certainly more informative than if we were simply told that instead of a confidence interval, that there was a p-value of 0.21. It doesn't really give us any information about the range of the likely range of the relative risk estimate of 0.7 to 2.6. So the fact that the confidence interval includes the null value tells us the p-value is greater than 0.05, but it doesn't actually give us the exact p-value. So if we want the exact p-value, we have to display that as well. So it's often the case, it's good to present both the confidence interval and the p-value, but the confidence interval presents more useful information, generally speaking. So how do we interpret the confidence interval? So the incorrect way to interpret it is if it was a kind of a equal probability across the range of the confidence interval, but that's not the case. So it's not like a flat distribution. It's a bell-shaped distribution, as you might suspect. So the closer you are to the point estimate in the confidence interval, the closer you are to the maximum likelihood estimate. So the probability increases as you get closer to the point estimate. So the outer bounds of the confidence interval, the true value is less likely to be at either of these two 95% confidence limit extremes. Now, something that's often overlooked by people when they're interpreting p-values and confidence intervals is the effect of bias, and so it's not right to ignore bias because it can have a major impact. And so illustrate it here. And so this could be, for example, the true estimate. So the relative risk is 1, in other words, the null value. So there's nothing really going on. There's no association between exposure and health outcome. And this is the confidence interval, which is determined by the sample size. So say you maintain the same sample size and you have a study which is biased. It could be selection bias or information bias or confounding. But the bias sends the relative risk in this direction and causes it the study result to be a relative risk of 2.5. It equally could have gone in the other direction, but for the sake of this example, we'll just say that the bias increases the relative risk. So it's not just the relative risk that gets increased, it's the confidence interval as well. And so the confidence interval, whereas for the true estimate, it included the null value, but with the bias, the whole thing got dragged in this direction. So now it excludes 1. It excludes the null value. So you might say you've got a statistically significant result, and you might think that say that this result is unlikely to have occurred by chance, and that may be so, but it has occurred because of bias. And as we talked about the correspondence between confidence intervals and p-values, so as we talked about, with a confidence interval that excludes the null value, that means the p is less than 0.05, whereas here it would have been greater than 0.05. So not only does bias have an impact on confidence intervals, it has a corresponding influence on p-values, which are really determined by the study estimate of the relative risk in relation to the null distribution. So you've dragged it in that direction, so it's gone way past the critical p-value, and your p is very low. So don't forget that bias has a big effect on p-values and confidence intervals. So just want to sum up the advantages, as I said, of the confidence interval over p-values. So the confidence interval gives you some sense of the adequacy of the sample size. So if you have a very wide confidence interval, then the sample size may be too small. If you have a narrow interval, which is kind of centered around the relative risk of your study, then you might judge that the sample size was pretty adequate. And so you can say that the confidence interval provides information on the likely true value of the effect measure, and gives you a plausible minimum and maximum value. But the p-value doesn't really provide any information on those things, not on the adequacy of sample size, nor on the range of possible values of the measure of association which you've obtained. I want to just describe to you the p-value function, because this is a way in which we can relate confidence intervals to p-values. So you can think of confidence intervals as being a nested series of confidence intervals. So we commonly use a 95% confidence interval. Sometimes we use a 90% confidence interval, but in theory there's an infinite number of confidence intervals going from well, we can never quite get to 100%, but and we never quite get to 0, but anything in between there, there's a nested series of confidence intervals, and they have a correspondence to a particular value of alpha, which is labelled here p-value, but it's really alpha. So a 95% confidence interval is equivalent to an alpha of 0.05, a 90% is equivalent to 0.1, and 80% 0.2, and so on. You can see the correspondence. So it's possible to construct a p-value function around any study relative risk estimate, and the width of the p-value function will be very much determined by the sample size. So it's, as I said, a continuous nested series of confidence intervals. In larger sample sizes provide the narrower p-value function. So you see that p-value function shrink. And they show this relationship between the alpha or p-values and their corresponding 1 minus alpha % confidence intervals. So this example here, an alpha of 0.1 is equivalent to a 1 minus 0.1 or 90% confidence interval. Okay. So this is just continuing that theme. There's in principle a 1-to-1 relationship between p-values and 1 minus alpha % confidence intervals. And so you would expect, based on what I've been telling you, that if you have a p-value of 0.05 from your study, then you would expect at least one of the bounds of the confidence interval to be 1. But sometimes you will find from your study results that that's not the case, and so you could get a situation like this, for example, where you have a p-value of 0.04, which seems like the confidence interval should exclude the null value, but in fact you see that it doesn't quite. It's got a lower limit of 0.98, or you could find something like this: a confidence interval which excludes the null value, only just, but the p-value is not less than 0.05, it's 0.07. So these sorts of results can occur because different statistical tests are being used in the software package to calculate the confidence interval and the p-value, and they're not exactly corresponding. And so there are some approximations used in some of the tests, and when you have this sort of these very close boundaries around the null value, then they may not exactly correspond. The way to get you shouldn't be too bothered by this. The way to get around it is usually to use exact methods of calculation of p-values and confidence intervals. So most of the statistical packages offer the options of exact methods for the calculations, and so if you choose those options, usually you'll find you've got p-values and confidence intervals which seem to line up together. But it can be disconcerting when you get results like this, but you just need to really revert to some using exact methods of calculation, just so that they line up exactly. Okay, I want to talk just very briefly about the multiple comparisons issue. We talked about the value, the alpha value of commonly 0.05, representing a so-called acceptable false positive rate of 1 in 20 test results. So you can imagine that if you carry out a whole lot of different statistical tests, statistical comparisons, then of those, 5% should have a false positive result, even if they really, the truth is that the null result applies. In other words, there's no association. But simply, just by carrying out at least 20 results, you would expect to get one of those showing a p-value less than 0.05 purely by chance alone, even if it represented a null, the truth was a null result. So how do we deal with that? How do we kind of distinguish false positives from true null results? And it's a bit difficult, but some people have proposed adjustments, such as reducing the critical p-value, so that you get much fewer false positive results. And biostatisticians often advocate an approach like this, and some of you may have come across, for example, the Bonferroni correction if you've done statistics. If you haven't come across that yet, you will do when you do statistics. So this to some extent is a difference in perspective between statisticians and epidemiologists. Most modern epidemiologists don't consider that it's necessary to make any corrections for several reasons. And this was best, I think, summed up by a paper by Ken Rothman, who's really been one of the leading epidemiologists of our era. He wrote this paper called "No Adjustments Are Needed for Multiple Comparisons," and that really says it all. We will make his paper available to you because it's definitely worth reading. And he says that basically we should not be concerned that we're carrying out many different tests, because often we have a situation, for example, where we have many different exposures, and we're testing each of those exposures against the health outcome that we're interested in. As often happens in case control studies, we have many different exposures, and so we look at them all separately against the health outcome. And then it's quite likely that one of them will end up with a p-value of less than 0.05. Conversely, in a cohort study, we may have many different health outcomes, and we may test one or a few exposures against those. For example, there are at least 100 different cancers that have been recognised, and so if we test all of those against our exposures of interest, then the chances are we're going to find a few results that just by chance alone appear to be excluding the null hypothesis. Should we take that into account, the fact that we're carrying out many tests? Rothman argues, I think very persuasively, that that's not the case for various reasons, some of which I summarise here. And the published results would be investigator dependent. And in other words, it would depend on the investigator how many tests they've carried out. And so you would get different results for different studies, simply because different investigators carried out different numbers of tests. And that would seem maybe not all that wise, because really there is a truth out there, and all of the investigators are trying to get at that. And so it shouldn't really be affected just by the number of tests that they're carrying out. Now, if we do carry out an adjustment by lowering the critical p-value, say from 0.05 to 0.01 or something much lower than that, then it starts to become so low that the very few, if any, statistical test results would kind of fall below that and end up in the null hypothesis being rejected. So we wouldn't find anything that wasn't a very strong risk factor for the disease. So we don't want to make our tests so insensitive that we're just not going to pick things up because we've made our critical p-values so low. And finally, and I think a very persuasive reason, we just don't base. We're not into the business of making firm decisions on the basis of one study. We want many studies, preferably of the same issue in different circumstances with different study designs, and then we're going to look for consistency of results across many different studies. So we don't need to be too focused on any one study and how many statistical tests we carried out. We're interested in the results of that study lined up with other studies. So we're going to talk about this this consistency consideration in a future talk. So my advice is don't be too worried about the multiple comparisons issue. It comes up a lot. Statisticians are often very concerned about it, but on the whole, epidemiologists are not so concerned. So I want to conclude this series really by just giving you some very brief and summarized guidelines for evaluating the role that chance might have played in producing the study results that you obtained or somebody else obtained. So now the very first consideration is whether or not the results could have been caused by bias. And this is critical because I showed you how low p-values and confidence intervals that exclude the null value could easily be caused by bias. So if you have a very biased study, then maybe it doesn't matter what p-values or confidence intervals you get, then it may not be interpretable. In any case, you want to avoid the statistical significance testing. In other words, making arbitrary decisions or making decisions based around whether whether a p-value is more or less than the value of 0.05. So I would say, unless you have to use it, such as in statistical power and sample size calculations, and also testing for heterogeneity of different strata in terms of whether or not you should combine them or not, I would avoid statistical significance testing altogether. Instead, use actual p-values, as we've already talked about. But because confidence intervals are more informative, I recommend paying most attention to them. But I would also say, if you can, and you're publishing a study, publish both the confidence interval and the p-value. But if you can only publish one, then just make it just the confidence interval, because it is more informative and also generally more acceptable to journals in epidemiology. Some journals, or at least one major epidemiology journal, at one point had a policy of publishing no p-values whatsoever, just confidence intervals, because of the problems of p-values. But now I think the policy has softened, and so that it's possible in some circumstances, such as the ones I mentioned, to be able to publish actual p-values, but they always want to see confidence intervals. So focus on them. Always consider the possibility of multiple comparisons, and in fact discuss it in the discussion section of your paper, but I would suggest that you don't make adjustments such as the Bonferroni correction just because you have done a whole lot of statistical tests. It's really not necessary because we're not going to make any decisions on the basis of one study alone. So which brings me to my final point. You need to take into account how the results of any one study, whether it's your study or somebody else's study, how consistent they are with other evidence, and also with any a priori hypotheses. Something which confirms an a priori hypothesis, in other words, a hypothesis that was put forward before the study was carried out, something that confirms that is much stronger than something which, a result that just turned up in a study but had no precedent and you weren't expecting it to occur. That's the sort of result that might be a result of a multiple comparisons situation, but of course that can be investigated in future studies. So we would then look for whether the studies were consistent. And even though an unexpected result might turn up in a study, it's something to be noted, and it could form the basis for a hypothesis in a future study. That's really very much how epidemiology operates these days. So that's the end of my 3 talks on random error. I've covered a lot in a relatively short time, and some of it will be a little difficult to come to grips with. It'll make much more sense when you have done some courses or a course in statistics, and really it's the most that in this class that I dig into biostatistics, but I really needed to make the link with biostatistics. So I hope that with a bit of familiarity with these concepts and perhaps reviewing the talks and the slides and reading the book, that some of these concepts which really are difficult will make good sense, and of course myself and the others involved in this course will be available to help you make sense of these things. So anyway, I hope it's been useful.